Hello everyone, this is Evani Porto speaking. I'm talking from Curitiba, Paraná. I'm a graduate student at Pontifical Catholic University of Paraná, Curitiba campus. My advisors are the professors Paulo César Felipe from PUC-PR and also the professor Stefan Henning Isotti from Federal University of Paraná. The title of my presentation is the partially saturated method for two-dimensional fluid flow past obstacles. My presentation is divided into 7 steps. Firstly, I'll give you motivation and importance, general and specific objectives, literature review, code structure and execution, check results, conclusions, and finally the next steps. As a motivation and importance, we know that in civil engineer applications, drag and lift coefficients are important to be determined. One method to preview the fluid flow effects is the use of computational simulation methods. The Lattice-Boltzmann method, LBM, is one of them. Below I have a picture of the Tacoma Narrows Bridge that failed in 1940 in the United States due to torsional effects on its structure. At the time, if you had some computational fluid flow simulation, we could identify that vortex will happen after the bridge profile, so the design could be changed at the time. But at the time they didn't such a tool like this, and we had big trouble in the past. But now we have these simulations tools, and we are very motivated to use it in our jobs during the development of engineering applications. So this is the motivation of this job. And the general objective is to validate a fluid flow simulation with LBM and PSM method for incompressible external flow. A specific objective is to implement the flow simulation code, analyze the convergence of the method for the simulation, pass the cylinder with Reynolds from 10 to 100, and finally compare the results of LBM and LBM with PSM method. As a literature review, I'm bringing here a picture of the simulation methods hierarchy. On the left side we have the macroscopic level, that is the continuum theory methods. So we have Euler, Rans, LES and DNS simulation tools. We have a computational reduction resources here because we have a macroscopic level, but we have a bigger complexity modeling here in this situation. In the middle, I have the LBM method, that's the mesoscopic theory based on the Boltzmann equation. This is the method based on physioscopic theories. On the right side, we have the methods based on the particle dynamics. So we have here a Knudsen number big enough to consider the movement of each molecule. So here we have increased the physical insight. But to calculate or simulate the propagation here is very expensive because we need too much computational resources. So the LBM method is chosen as a good option to simulate the fluid flow because they can bring the behavior of continuum theory by the use of mesoscopic theories in a very easy way to implement. So the Boltzmann equation is chosen to be used. This method has started in the 19th century. Basically, the first insights was done by James Clerk Maxwell. He stated that a large set of molecules of different speeds collides with each other, and the result is the conservation of moment. Later, Ludwig Boltzmann stated his constant, the constant of Boltzmann, and this constant was added in the James Clerk Maxwell equation. Then we have the Maxwell-Boltzmann equation distribution that takes in consideration the energy of the molecule, the mass, the number of molecules, and the fluctuation speed of the particles. So by integrating this equation, we have the total expected number of molecules at position x and time t. But for this equation, we need to add a collision operator that will represent the changes in speeds and positions of the particles. We needed this relaxation time in the use of the collision operator. I'm using the BJK collision operator, and the equation of Maxwell-Boltzmann will be described like this. And this equation replaces the Navier-Stokes equations in CFD simulations. and it's possible to obtain the same Navier-Stokes equations from this one. So to simulate, we need a discrete equilibrium distribution. This discrete equation was done by Dumier, that considered a second order on the variable u here, that's the velocity, and he started to use the square weights and the speed of sound in discrete terms. This equation can also be used to obtain the Navier-Stokes in the same way. This equation can be used to simulate models in 1, 2, and 3 dimensions. I'm using 2-dimensional fluid flow simulation. We have here an example of lattice sites with 9 speeds, and each one with the specific square weight. This is the numerical domain that I'm using. We have here 500 lattice sites for the vertical axis and 1200 lattice sites for the horizontal axis. The dimensionless speed and diameter of the obstacle is kept constant. And with these two variables kept constant, the relaxation time stays in function of Reynolds number, basically. So if you have an increasing of Reynolds number, the relaxation time will be decreased. The code structure has some stages. At the beginning we have the initialization, where we assume some values for the first equilibrium distributions. Then the calculation is done for the equilibrium populations. After have the collision step using the BJK operator, the streaming step, boundary conditions, and as outputs we have the specific mass, velocity field, drag and lift coefficients. For boundary condition, I'm using the Zuihe condition for the unknown populations that must be calculated by the use of the known populations. These calculations we can use for superior and inferior boundaries, or implement a periodic condition for these unknown populations. For the outlet, we can use the penultimate distributions to find the unknown populations of the last column. For the boundary condition on solid interface, I'm using the halfway bounce back that considers the streaming step at half of the distance between the fluid sites and solid sites. So the populations are turned back to the opposite direction at time t plus delta t by 2. So at time t plus delta t, the distribution are in the opposite direction. And by summing the positions in the first direction and the opposite direction, we have the total force on the solid interface, for example. But in this system, the frontier site is part of the fluid, and the surface ruggedness is the source of errors in numerical simulations. So to improve this condition, we have the PSM, that is the partially saturated method. This method numerically smooths the ruggedness of the square sites used in the simulations. So by each site we have a solid diffraction. For example, for this site we have a 70% of solid portion for this site. All the sites has a value between 0 and 1, and this value can be used to calculate the weight parameter. So this weight parameter is used on the collision operator. Then we have a special collision operator for solid sites and the standard one for fluid sites. The operator for solid sites consider the populations that were bounced back during the collision, during the streaming process, and this is a special one to calculate the equilibrium condition in the PSM method. So the key point here is how to calculate the specific areas for each site. We defined in our job 4 different areas to calculate the specific value. So green areas, blue areas, orange areas, and yellow areas has a specific equation to calculate the value, respectively value. So after calculating these boundary conditions, we can get the outputs of the program. That's the velocity field drag and lift coefficients, and also the Sturhall number. As a check results, we have here the velocity fields for henodes ranging from 10 to 100. For henodes of 40, we have a laminar flow, and for henodes around 100, we have the oscillations in the fluid flow. And here we have the variation on drag and lift coefficients. So here I have the values in comparison with other authors and also experiment tests. The simulation was good and we have good values with BJK operator. But using the BJK with PSM operator we have better results and we have a better agreement with values of the literature. So the PSM method is good to get more accuracy results without the need to increase the numerical domain. So it means a reduction in costs, for example, computational simulation costs. Here I have a graph of the lift and drag coefficients. On green I have the lift coefficient and in red you have the drag coefficients. So we have variation of these values because of the vortex occurrence behind the cylinder for henodes of 100. So this is the representation of the fluctuations in drag and lift coefficients. So this frequency of vortex has a value, we got these values in this program. And for henodes around 100 we have a frequency around 0.2 and the Sturhall number is 0.17 for henodes 100. These values are also compared with the literature results and it's in a good agreement. It was done for henodes 80 and the henodes around 60. The values are also in agreement with the literature. So as conclusions, the developed code can execute the LBM and BJK and also the modified BJK method. The method presents accuracy with reference values of drag and lift coefficients. All of them are in a consistent of literature results, and the benchmark study reveals a better agreement of the results with PSM. And everything that we found here with PSM means that applying the PSM method to smooth the staircase on solid surface avoids the increasing of the numerical domain resolution. And considering that increasing has a significant impact on computational costs, the method can be considered as a fair alternative to save expense on computational simulations. So the PSM method enables us to get better results without the need to increase the numerical domain. This is the key point of this method. And as the next steps, I want to apply this code in a case study of bank of cylinders to identify the effects of the arrangement of several solids, of several cylinders here in the numerical domain. So that's it. Thank you for watching me, telling a little bit about my job, my presentation, and now I'm able to answer some questions and also clarify some doubts. Thank you for watching. That's it for a while.